The Coherence Conundrum, Methods for Measuring Lectal Coherence. Since Guy's 2013 thought-provoking study investigating the cognitive coherence of sociolects, considerable debate has ensued as to whether the statistical construct of covariation, that is, the correlation of multiple linguistic features, constitutes sociolectal coherence. In recent years, much research has focused on modeling coherence across a number of language varieties, using diverse methods with decidedly mixed results. Some studies show high degrees of coherence, and others only a modicum, and still others show no coherence at all. Hence, the research questions this paper attempts to address are: how should coherence be modeled and measured? How much coherence is actually required for a lect to qualify as coherent? And what can different levels of coherence tell us about language change? To investigate these questions, this study evaluates the use of Swabian, or Schwäbisch, a High German dialect belonging to the Alemannic family, which is spoken by just over 800,000 people, or 1% of the German population. Two communities are considered in this research: the large international city of Stuttgart and its surrounding suburbs with over 1 million inhabitants, and the mid-sized town of Schwäbisch Gmünd and its surrounding rural villages with about 60,000 inhabitants. This research combines both a trend study and a panel study based on data collected from 40 speakers recorded back when I was a PhD student in 1982, stratified for education, gender, and age. After a 35-year hiatus between 2016 and 2017, I collected data from over 100 additional Swabian speakers, 20 from 1982 who were re-interviewed and comprised the real-time panel study. I've also selected 40 other speakers from the 2017 recordings who can be considered social twins with the 20 panel speakers in terms of age, sex, education, and community to create the real-time trend study. The twin speakers are matched for age, sex, education, and locality, providing an 84% overall match with the panel speakers. 20 linguistic variables were selected as typical in Swabian and other Southern German varieties, covering phonological, morphosyntactic, syntactic, and lexical features. Each has been coded for a binary distinction between the dialect variant and the standard German variant. Obviously, I'm not going to walk through a description of each variable, so I refer you to my website for further information. The methods used in the study consist of semi-structured sociolinguistic interviews conducted by native Swabian speakers with me in attendance in the role of a friend of a friend. To increase compatibility across the years, the same survey instrument and interviewing techniques were used in both 1982 and 2017. Two social factors are considered in this paper: recording year and community. Quite clearly, there's no single best measure or generally agreed upon set of conventions for measuring coherence in the dataset. According to the statistician George Box, all models are wrong, but some are useful. So I'm going to talk about 4 different statistical methods, 3 of which have been extensively used by sociolinguists for evaluating coherence, and show how the combination of multiple methods can yield a more robust picture of the linguistic situation. Correlation analysis, multiple regression analysis, principal components analysis, and a new construct I call the lectal lattice. So correlational analysis is a method of statistical analysis that evaluates the strength of the relationship between 2 or more numerically measured continuous variables like age and dialect use. The theoretical basis for this approach is that groups of speakers who are consistent in their frequency of dialect or standard use will exhibit high levels of correlations across variables. However, if variable usage is ad hoc or influenced by personal, contextual, or other situational and interactional aspects, then speakers will exhibit a random mix of high and low correlation indices. It's from Guy 2013. While this approach is particularly useful for establishing significant connections between variables, the disadvantage is that it cannot make any inferences about the relationships among variables. So an effective way of looking at correlations is through a correlogram, a graphical construct that depicts the sign, that is whether variables are positively or negatively correlated, the scale, how strongly or weakly the variables are correlated, and the relationships between the variables. That's the clustering of similar variables together. So these 2 correlograms show the correlations between the dialect variants for the 20 linguistic features in 1982, separated by community, Schwäbisch Gmünd on the top and Stuttgart on the bottom. The variables are ranked from the highest correlation coefficient to the lowest, with positive correlations in the upper left represented by darker shades of blue, and negative correlations in the lower right by darker shades of red. Significant tests for each pair of variables were conducted at a 0.95% confidence level using Spearman's rank correlation coefficient. It's easy to visualize from the shading that the Stuttgart variety is more coherent in 1982 than the Schwäbisch Gmünd variety. And here are the corresponding correlograms for the same 20 speakers in 2017. From the visual alone, we can easily see that both sociolects have become more coherent by 2017, particularly the Schwäbisch Gmünd lect, which appears to be nearly as coherent as the Stuttgart lect now. And this table presents the actual correlation metrics so we can quantitatively assess just how much more coherent these lects have become over the years. The first row shows how dialect density declines across the 4 sociolects, and the third row shows how the correlation mean increases. These metrics indicate that lower dialect density, which results in a more uniform standard variety, rather than a variety that mixes dialect and standard language variants, is more coherent, which of course makes intuitive sense. I'd like to point out one other correlation metric in this table that linguists have used in the past, the percent of significant pairs. That is, the percent of variable pairs that show significant correlations. The larger the values reveal a greater number of correlated variables. But I don't find this metric particularly enlightening, as it's not merely the number of correlated variables, but the depth of the correlations. As you can see, Stuttgart in 1982 has the greatest number of correlated pairs, 63%, but it's not really any more coherent than the other 2 lects, which show a correlation mean of around 5%. Interestingly, the apparent time results in the twin study do not mirror the real-time findings from the panel study. In fact, there's been considerably greater change in coherence across the lifespan from the previous slide than across the generations, as this slide shows. While dialect density has dropped for the younger generation in Stuttgart, it remains strong in Schwäbisch Gmünd, and the level of coherence based on the correlation mean is relatively comparable across the 4 sociolects. It makes one question if correlation mean is really suitable for investigating coherence across lects. It's interesting to look at which variables correlate in each of the lects. For example, neg, the negative particle net versus nicht in Swabian, correlates the most with the other variables in the lect of the Stuttgart younger generation, but it shows fewer significant correlations for the younger generation in Schwäbisch Gmünd. This introduces the question, what is the social meaning of this variable in the different communities? A topic which must unfortunately be deferred to another talk. The second approach for modeling coherence is multiple regression analysis, which estimates the relationship between a single dependent variable and one or more predictor variables. Both linear and for numeric variables such as speaker age and dialect use, as well as linguistic regression for classes of events such as speaker sex, age group, socio-demographic class, and so on. So first I want to point out that the 20 linguistic variables I'm looking at are of different types, that is, different etymological origins. Swabian is part of the Alemannic dialect family, which means it has many of its own dialect features, but also shares features with other Alemannic and High German varieties. I've coded each of the 20 linguistic variables for Swabian only, Alemannic, which includes Baden and Switzerland, or regional, covering variables originating from from other geographical regions in Germany. So these plots display the results of the multivariate modeling based on the type of linguistic variable. Counterpose the Swabian specific variables and Alemannic together against the regional ones. Looking first at the regional features across real time in 1982, no significant differences are evident in the level of covariation between the communities. The purple box for Stuttgart and the turquoise box for Schwäbisch Gmünd completely overlap. However, by 2017, a difference has emerged, most notably in Stuttgart, which shows an increase in covariation between 1982 and 2017. This difference is likely the result of speakers' greater convergence to the standard language. A similar situation is visible in apparent time, with the younger speakers in Stuttgart showing greater covariation with the regional features, although the younger speakers in Schwäbisch Gmünd show lower covariation than their older cohorts. For the Swabian specific features, Stuttgart already exhibited a very high degree of covariation in 1982, and by 2017, Schwäbisch Gmünd is following suit and converging with Stuttgart. Both studies reveal significant differences in covariation between the regional and Swabian features by community, providing support for the hypothesis that Swabian specific features cohere more tightly than regional ones. I attribute this tighter coherence to the common socio-historical background of the Swabian features and to the speakers' desires to mark their group membership, i.e. their Swabianness, facets that cannot be conveyed with the more broadly used regional features, which have spread into Swabian from other regions in Germany. The third approach that linguists have commonly used for modeling dialectal coherence across time is principal components analysis. PCA is an exploratory data reduction method that reduces the dimensionality of the data through orthographical transformations, such that the greatest variance lies on the first principal component, the second greatest variance on the second principal component, and so on. So these plots depict PCA for the 20 linguistic variables, the real-time panel study on the left and the apparent time twin study on the right, purple for Schwäbisch Gmünd and turquoise for Stuttgart. Dotted lines represent 1982 or the older speakers, and 2017 are represented by solid lines, and as well as for the younger speakers. The 1982 Schwäbisch Gmünd speakers, shown by this small dotted purple box, demonstrate the tightest coherence, the least variability, followed by the 1982 Stuttgart speakers, shown by this dotted turquoise box, with no overlap, signaling two very distinct linguistic varieties. The extensive dialect leveling which has been occurring in Swabian over the last 35 years has resulted in a fusion of the two varieties by 2017, which can be seen by these two solid line boxes, clearly revealing a significant merging of the two varieties. The results from the twin study signal a different but congruent picture. The older speakers in both Stuttgart and Schwäbisch Gmünd are more similar to each other, as are the younger speakers, demonstrating that apparent time change does mirror real-time change. However, lifespan change for the panel speakers also appears to mirror real-time as apparent time, as reflected in these two generations of 2017 speakers. So the fourth model for assessing lectal coherence is the lectal lattice. This pizza illustrates the concept of a lattice, in which you can see there are any number of subsets of variable toppings you could have. In this example, there are mushrooms and onions and peppers, which of course you can have in any combination or alone. And of course, you can have a pizza with no toppings, like a dialect speaker who speaks only standard German at school. So linguists have used lattices in phonology, syntax, semantics, neurolinguistics, computational linguistics, but not yet in sociolinguistics or variation studies, to my knowledge. So a lattice is an abstract structure based on the order theory of mathematics that uses binary relations to examine the hierarchical or implicational relationships within a given set of elements. It generalizes the data from a straight line, such as X implies Y implies Z, to a multidimensional picture depicted by a Haas diagram. The lattice consists of partially ordered sets called posets, in which every two elements has a least upper bound called a join and a greatest lower bound called a meet. The relationship between the variables is one of inclusion. For any two elements, you can go up the lattice to find an element that includes both, the join, or go down the lattice to find an element that includes both, the meet. Lattices exhibit the principle of duality, which means that they function equally in both directions, top down or bottom up. Thus, in turning a lattice upside down, the meets become the joins and the joins become the meets. So the first step in developing a lectal lattice is to create post hoc pairwise comparisons called a poset for the 20 linguistic variables arranged in 2x2 contingency tables, which create a poset of 56 pairs of variables. Using the Suisse and Schuster exact test with the Holm-Bonferroni method, each pair of variables is tested to determine the significant differences in frequency of use. When a statistical difference is found, that is when the variable in the row is lower than the variable in the column, maintaining the implicational order, that pair is assigned a 1. If there's no significant difference for that pair, it's assigned a 0. In a poset, every pair of variables need not be related significantly for the pattern to be valid. This allows for uncertainties or inadequacies or unknowns in the dataset, which of course is common with sociolinguistic data. In the next step, the speaker's posets are sorted by significant pairs and the frequency of the dialect variant, generating a new sorted poset. The posets are assigned a rank by summing the significant pairwise comparisons. Angela in 1982 has a rank of 95 because there are 95 significant pairwise comparisons in her poset. In the next step, neighboring posets, those that are most similar, are joined. That is, all neighbors that lie at the same minimum distance are joined one by one. In this example, showing the 12 Swabian specific variables, Angela's poset is joined with Market's poset, and we get a new poset, which becomes a node in the lattice. The number of pairs that were joined between the two posets, highlighted in yellow, is the mathematical distance between the two lects, 6 in this case. The distance between the two lects represents the number of pairs that would have to change in order for the two lects to be a perfect match. To build the lattice, all the posets are connected in this way with their nearest neighbors and joined into larger groups. It's posets within posets, or turtles all the way down, I like to say, and up, of course, to maintain the duality of the lattice. So here's the lectal lattice for the 20 speakers in 1982. The vertical axis represents the rank, the hierarchical distance between the lects, and the horizontal axis represents the file, the left to right lineup of the individual lects, which has been determined based on the first principal component. The lattice was created with standard R functions such as plot, points, lines, and text, It's technically a sublattice because it doesn't show all the points in the lattice, rather only the significant ones. It's also a semi-lattice because it depicts only the joins or the upward trajectory. This sub-semi-lattice greatly simplifies the visualization by eliminating redundant and irrelevant information. It's important to point out that each point in the lectal lattice represents a lect. The points for each speaker's idiolect form the foundation of the lattice. These are labeled with the speaker's names, turquoise for Stuttgart and purple for Schwäbisch Gmünd. All points above the idiolects represent different groups of similar speakers, such as a dialect, a sociolect, a regiolect, or perhaps a certain style or register. From this picture, we can see that the speakers plainly fall into two distinct groups, those from Schwäbisch Gmünd and those from Stuttgart, with only one exception. Emma is one of the oldest speakers in the study. She was 55 in 1982, completed only elementary school, and her dialect contains many traditional Swabian forms, which are more in line with the conservative variety spoken in Schwäbisch Gmünd. Turning to 2017, this plot presents the lectal lattice for the 20 panel speakers 35 years later. A large group of Schwäbisch Gmünd speakers is still visible on the left. However, on the right, speakers from Schwäbisch Gmünd have fused with those from Stuttgart, demonstrating the merging of the two varieties and the formation of a new super-regional variety. The lattice demonstrates that the Swabian dialect is leveling, changing from a geographical or horizontal variety to a sociolectal or vertical variety, as a result of the extensive social and demographic transformation taking place in contemporary German society. And here's the lattice for the twin speakers. As with the previous lattice, the twin speakers show similar mixing and lectal fusing among the Stuttgart and Schwäbisch Gmünd speakers, demonstrating that apparent time change mirrors real-time change. The lectal lattice produces results similar to the PCA, albeit with a different graphical representation. Both approaches reveal two distinct lects, Stuttgart and Schwäbisch Gmünd. Both PCA and the lectal lattice are data reduction methods that unveil significant groupings of speakers based on linguistic factors alone. One advantage of the lectal lattice over PCA is the graphical display. The hierarchical depiction of related lects exposes the underlying relationships between lects without dissecting multiple principal components and drawing ellipses or rectangles to identify specific groups of speakers. Another crucial advantage of the lectal lattice over PCA is in the calculation of the distance between the lects. With principal components, distance is calculated based only on the frequencies of the variables. With the lectal lattice, distance is determined based on both the frequencies and the implicational order of the variables. However, the ultimate advantage of the lectal lattice is the ability to calculate, measure, and compare how closely different lects and groups of lects cohere, and that is done through an approach I call implicational coherence. Implicational coherence is a method for assessing the level of coherence in any given lect by calculating the number of significant pairwise comparisons that follow the implicational pattern. In this example, there are 60 significant pairs above the diagonal with 6 deviant pairs below the diagonal, yielding an implicational coherence of 82%. The objective is to provide a method to assess whether more coherent lects are less susceptible to change, and conversely, whether less coherent lects are more vulnerable to change. So these plots show the lectal lattices for the 20 panel speakers by community and recording year for the 12 Swabian specific variables, which, as we've seen, pattern differently from the more broadly used regional ones. In 1982, Schwäbisch Gmünd shows an implicational coherence of 80% and a dialect density of 61%, while Stuttgart in 1982 shows an implicational coherence of 59% and a DDI of 48%. By 2017, dialect density has declined 8% more in Stuttgart, from 48% to 27%, than in Schwäbisch Gmünd, from 61% to 47%, providing support for the hypothesis that the less coherent variety of Stuttgart is more susceptible to change than the more coherent variety of Schwäbisch Gmünd. The supposition underlying this premise is that strong coherence binds linguistic variables together, making them more resistant to outside influences, much like the strong ties in Milroy's closed social networks, which resist outside innovation. This investigation in coherence in Swabian has probed 4 different methods for analyzing the orderly heterogeneity of sociolects and the change in coherence across time. As the results from these analyses show, there's no silver bullet for assessing sociolinguistic coherence. Each of these methods has unveiled disparate aspects of a highly complex, multifaceted, and nuanced phenomenon. As George Box claims, all models are wrong, but some are useful. It's about investigating different models and triangulating the results to provide a holistic explanation of the situation. Correlograms provide a useful tool for demonstrating correlations between variables. However, they cannot draw inferences or predictions about the relationships among the variables. Multivariate analyses model both dependent and independent variables, along with the interaction effects, indicating the most significant factors constraining the variation. PCA presents a multidimensional view on how variables cluster. However, the researcher is left to interpret the effect that the independent variables have on the clustering. And the lectal lattice also provides a multi-dimensional view, showing the hierarchical ordering of lects based on significant pairwise comparisons, the implicational ordering of the variables, and the variable frequencies. It can be utilized to construct a model that visually illustrates how close or distant individual lects are from one another, for both individual idiolects as well as for groups of lects. All of these models support Weinberg, Labov, and Herzog's contention that coherence or orderly heterogeneity is found in the aggregate grammar of the speech community, reinforcing the widely held premise that individuals in the community behave in parallel, reflecting regularity and coherence. Thank you.